it's time. So let's continue. Just a reminder, no classes on Wednesday due to Thanksgiving. Okay. Where were we? Here. Okay. So we were talking about the Laplace transform. We talk about the definition and the connections with Fourier analysis. So basically, this is the real part of the thing, and the Fourier analysis is the imaginary part of the thing. So this part takes care of the exponentials, and Fourier takes care of the sine and cosine terms. Okay, so we did this one, and we did several examples. We talked about exponentials at first, because this is so popular. A lot of the solutions we have done so far for ODE is exponential. So of course we need this. And we find this is actually very easy to solve. So we find the Laplace transform is given by this, but only for s bigger than a. If s is less than or equal to a, when you take the limit to infinity, you will find that the whole thing does not exist. So due to this infinity here. That's what we did. We also did number one, that is for constant function. We found it's 1 over s. But now if you think about it, actually this is very easy to do. These two are actually the same formula, because if you take a equals 0, you have L e to the 0t, which is L1, and you will find it's actually the same formula as this. Okay, so we can actually forget about this one. If you see 1, you can just treat it as a special case of exponential function. That's all we did so far. Then we talked about several properties of Laplace transform. The first most important one is it's linear. That means it will be very, very easy to use Laplace transform to solve linear differential equations. And for nonlinear, it's not straightforward, even if it's doable. Second, probably the most important, when you have a derivative, you can change it to be s Ly minus y0. So two things. Number one, this one will treat a derivative really nicely. So we don't have to worry about the derivative anymore. If you see a differential equation which has a lot of derivatives, just do the Laplace transform. Once you do it, there will be no derivative left, only Ly. Second, this y0 here has something to do with the 0 here. So that's by convention, we take it to be going from 0 to infinity, not any other number going to infinity. Okay. And the reason is because we want to utilize the information we know about the initial condition for the equation. Okay. With these two in mind, we try to solve a differential equation. Actually, not a differential equation, an initial value problem. Y prime equals 2y. Y0 equals 200. Okay, the answer is going to be yt equals e to the 2t times a constant, and with the initial value, we know it's 200 times e to the 2t, which is great. Now, if we solve it using Laplace transform, then we just want to apply Laplace transform on both sides. We have s Ly minus y0. This comes from integration by parts. And then linear property for this one, we finally can put Ly all together equals y0 divided by s minus 2, which is 200 times y. Okay. finally, what we want to do now is we want to find y. Instead, we have ly. So now if we think about it, what kind of function if we put in, we're going to have 1 over s minus 2. Automatically, we think about this. We just did this one. Okay, if this is true, then if ly equals 200 1 over s minus 2, I'm very likely wants to say y equals basically 200 by linear property times e to the 2t, which we already know it's the solution, so this is actually valid. Okay. But now it gives us a question. That is, if you know the Laplace transform of some function, can you transform them back? Can you transform them back into the original function, which involves the inverse Laplace transform. Okay, if you know L e to the t, 2t, equals 1 over s minus 2, and you know Ly equals 1 over s minus 2, can you just say y equals e to the 2t? That clearly involves taking this one and try to inverse it. Okay. We don't have the tool to actually tell you if it's right or wrong. Okay. But what we can say is the inverse is unique. The Laplace transform is unique. Moreover, the inverse of Laplace transform is linear. That means if you have something which is 200 times 1 over s minus 2, you can actually take the 200 out and just do L inverse 1 over s minus 2. And because the inverse is linear, you can actually try to say this, because if this one satisfies that, the inverse will be this one. Okay, so these two are very important, because every time you do a Laplace transform of ODE, your answer will be LF. But once you know LF, how do you find the original F? You will need to use this. Okay, so these two are very important. Sounds good? Okay, so we can actually go ahead and try to say the answer is this, because if you know the Laplace transform is 1 over s minus 2, and you know e to the 2t satisfies that, then it will be e to the 2t. Okay, it's not hard to see. If L is linear, this implies L inverse is linear. For sure. Okay, and also if L is unique, think about it, L is a linear operator, or let's call it linear transformation. Okay, what do you mean by a linear transformation? Oh, no, not what do we mean. What property do you have for linear transformation? If you want to show it has an inverse, you just need to show this one is 1 to 1. How do you show a linear transformation is 1 to 1? Because it's linear, you just have to show the kernel space is just the vector 0. Okay, that's all you need to show. Now, if you think about this, that's very interesting to see, because what kind of function if you put into the Laplace transform will give you 0? Due to the non-negative property of e to the negative st, this yt has to be 0. Okay, this will force it to be. We won't prove this, but this is why. Okay, the only function if you put in that if you take the integration from 0 to infinity, After it times by e to the negative st will always be the zero constant function. Okay, so that's why it's unique. And linear is probably very easy to show. So that's nice. Okay, with the Laplace transform and inverse Laplace transform, now we have the general way of solving ODE. Say you have ODE. Okay, it has y prime, all those kind of things. Okay. Now what you can do is you can take the Laplace transform. Once you take the Laplace transform, solve it, your final answer is going to be Ly. No y prime, no y prime prime, because you can always change it. Become a function of s. Finally, do one more step. That is y equals L inverse y over s. That will be your solution. Okay. Moreover, your initial value will be used here. Because when you take the Laplace transform of a derivative, you do need y0. So technically, this one is used to solve for an initial value problem. Okay, that will be the key part of how to use Laplace transform in solving ODE. Sounds good. Okay. Even if you don't have the initial value, you can still find the general solution in this way. For example, like the one before. What if you just want to solve this? But you're looking for the general solution, not, I don't know the initial value. I don't know y0 equals 200. It's actually very easy to do. What you do is just you manually add one more thing. That is your initial value. Since you don't know it, you just say it can be any constant. Okay. Now, if you do it, okay, and then SLY minus y0, but you don't know it, so just make it a constant. C divided by s plus 2. This implies y equals c times e to the negative 2t. Okay, so even if you don't know the initial value, actually you can just name the initial value yourself. That thing automatically become a constant, which you can put into the general solution, because the general solution has some constant inside, right? It can be anything. So that's how you do it. Okay, let's just try to do one more example. Y minus 4 e to the negative t. Y0 equals 1. Okay, how do you do this problem? If you don't know Laplace transform, you probably want to do this. Okay, after that you find the integrating factor on both sides, and then you go ahead. So this one can be done by integrating factor. But now with Laplace transform, we can do it in a different way. Laplace transform. So okay, now S Ly minus y0 equals Ly, and you do know the Laplace transform of this, which is 1 over s plus 1. 1 over s plus 1. Okay. Now this is 1. SLy minus Ly equals 1 minus 4 over s plus 1. So Ly will equal 1 over s minus 1 minus 4 over s plus 1 divided by s minus 1 again. Okay. Now the only thing left is try to write down y equals part 1 minus part b. This 4 is no problem, okay? Do you know the inverse transform of this? Well, it's e to the t. Because if you take e to the 1t, you will have 1 over s minus 1. Then the inverse function will be this. Now what about the inverse function of this? Remember, the 4 is not a problem. The key problem is you don't know this. The only thing you know is actually something look like s plus a. Okay, which you know that it comes from e to the at. Then the question becomes, can you take this one to make it a combination of linear terms, not quadratic on the bottom? Do you remember this in calculus 2 when you take the integration? This one can be split into this, right? Okay, partial fractions. Okay, go ahead and try to test it. You will find this one is going to be 2 and the negative 2. I skipped the parts, the details, but it's basically partial fraction. Okay, if that's the case, I just need to do L inverse these two, which will be negative 2 times e to the negative t, plus or minus. Plus 2 e to the plus 2 e to the t. Yes, okay. Which give me negative e to the t plus 2 to the e to the negative t. Maybe it's nice for us to switch the Sounds good? Okay. For now, the only thing we know is actually the exponential. So you're looking for partial fractions. You're always looking for 1 over s plus a. But you can imagine how powerful this thing is. Because later, maybe for something else, you will have some sine, you will have some cosine, you will have some x squared or whatever. But as long as you know the Laplace transform of those kind of things, you can always do it. And once you finish, you have Ly equals something involving sine x, cosine x, or x squared. As long as you know the inverse transformation, you can always transfer them back. Okay, so the key here is just knowing the transformation, knowing the property, and finally doing some algebra. So calculus become algebra. Okay. We have done this actually a lot of times before. We just didn't actually call it a transformation. That is, if you try to solve some problem in one domain and you find it super challenging, what you can do is you can find a transformation to transform it into some other domain, solve it there, and then suddenly everything becomes easier. Okay, so that's the power of transformation. I will give you several examples, and then you will see the general picture of how to do those kind of things in general. Number one, you have A, which tells you a linear transformation. What you can do is actually you can do this. So if you pick a different coordinate system, suddenly the originally complicated transformation becomes super easy. Okay, this is a transformation if you do the standard base. This will be the transformation. Actually, not this, just this one will be the transformation if you do it in eigenvector basis. So if for the same thing, if you just choose a different basis, suddenly your matrix becomes diagonal. The determinant is easy. The invertibility is easy. The eigenvalues are easy. Everything becomes super easy. Okay, that's the idea of transformation. Second, here's a line. But somehow you can transform it into y equals ax plus b. Solving some problem here can be challenging, but if you solve the same thing here, it can be super easy. So what you did is actually transform the geometry into algebra. I know we keep telling you that's the same thing, but they're not the same thing. On the left, you have a shape. You have a line. On the right, you have a linear equation. They're not the same thing. But mathematically, they have some kind of connection. And that is a transformation you used. Sometimes it's easier to do things in this way. Sometimes it's easier to do things in this way. But now you have the freedom to transfer between two domains. Okay. Similarly, the next thing you can think about is a function. And then you go to the Fourier transform. What you did is actually you did going from time domain, and then you go to the frequency domain. You have the signal, but you have two different ways of describing the same signal. Number one, you can describe it as what you see in the signal. At time t, the signal is this. At time t, the signal is this. Or you have a different way to describe the same signal, just using a different language, using the language of frequency. Then what you need to tell people is actually, okay, the signal is a linear combination of a lot of sine and cosine curves with different frequencies. Okay. Sometimes it's easier to do things in this way. Most of the time, it's easier to do things in this way. Sounds good? Okay, so that's the idea of transformation. So if you see some complicated ODE, maybe it's super difficult to solve, but once you transform into something else, you find, oh, all the calculus are gone, derivatives are gone. Algebra become the key. Okay, so that's the power of transformation. Hopefully from now on, for everything else in advanced physics and mathematics, you will be able to adopt those kind of ideas of transformations. Every time you try to talk about something in a different language, you're doing a transformation. Okay. Of course, eventually you will be able to actually study the transformation between two objects. That becomes a much higher level of mathematics. You're talking about mapping. That's where functional analysis, topology, and everything is doing. Okay, mapping theory. Technically, it's not a theory, but I'm just going to call it a theory. All right. Is everything clear for 6.1? All right, let's move on to 6.2 then. Discontinuous function. Well, we did a lot of things before. We have a lot of ways to solve a differential equation. Why do we need another way? I mean, Laplace transform is nice, but we do have a lot of ways of solving it. Okay. The good thing about Laplace transform is when you have something that you cannot solve before, when you have something involving discontinuous functions. For example, you have this. Existence and uniqueness requires Fy is continuous. Actually, I put Fty here. That's the general case. Requires Fyt is continuous. Okay. And for uniqueness, you need, let me just write it down. Partial F, partial Y is continuous. This is the requirement for existence and uniqueness. Okay. Now, of course, if this one fail, that means your function is not continuous. You cannot use the existence and uniqueness. It will make everything super hard to solve. For the worst case, this is a very bad function, and then there is no way you can find a solution. Still okay? But now what we wanted to talk about is something kind of in between. It's not too bad, but it's not continuous either. We want to talk about something which is discontinuous, but not so bad. Okay, for example, if you have a function like this, is it continuous? Not really, but it's not so bad. Why? Because it's only discontinuous at a one jump. Okay, so what about this? Number one, if you do it pointwise, it's bad because you have discontinuity. Everything you had before cannot be used. But do you remember in calculus, there is some kind of operation you really don't care about finite jumps? Do you remember? That is when you take the integral. Pretty nice. Can you take the area under this curve? Can you integrate this function? Yes. Just integrate the left part, integrate the right part. If there is a discontinuity, really when you try to care about the area, that one point really doesn't matter. Actually, if you just have finite places where you have a jump, it doesn't really matter. Sounds good? Okay. That means if you want to handle this differential equation in this way, you cannot do it because it's not continuous. But if you can somehow to take the integration on both sides, the small discontinuity will be gone because integration doesn't care about that. Still okay? What is a Laplace transform? It's an integration. Okay? Therefore, discontinuity, like this, can be handled by Laplace transform. Why? Because I take the integration when I do the transform. F, y, ft, dt. Therefore, discontinuity is not a problem. Sounds good? That's the idea. Of course, we want to talk about why do we need discontinuities in a differential equation. This is called a Heaviside function. I better make it careful. It's actually one word. Which look like this way. U, A, T, 0 for t less or equal than A, and the 1 for t bigger or equal than A. Which basically look like this. So there is a circle here. It's a function. It's 0 from 0 to a, and it's 1 from a to infinity. Okay. Now, what's special about this one? Why do we need it in real life? Well, you can easily think about a case like this. Okay. Then, your right-hand side of your dynamics is not continuous anymore. From 0 to a, you have this. That's a differential equation that gives you some kind of dynamics. But starting from a, you have something else. Okay. So it almost feels like this one is going to serve as activation or kickoff. Of your differential equation. Can you think about some examples in real life? Something just, does not have any effect until you trigger it. It's very common to see, right? For example, if you're trying to launch a rocket, what's going to happen? Well, the rocket is going to actually fly with a differential equation, of course. Good so far? Until the first level just get exhausted and just drop. Suddenly, the whole dynamic change. Okay, you have the second level, and then the third level. From here, you can see, okay, at first you have a differential equation, but after a certain time, it changed to a whole different differential equation. Part of it will be the same as before, but also part of it will be added on top of that. That is actually captured by this Heaviside equation to tell you, okay, starting from here until time a, I'm going to start a second kind of dynamics. Sounds good? All right. So that's actually very common to see. In real life, actually, it's very common for you to see several terms like this. Okay, one just got activated, and after a while, that one got dropped, and then another one got activated, or maybe they are activated together. Okay, so you can play with it to try to make sure that the system describes what you want by manipulating A and this UA. But what difficulty does it bring you if you just try to, try to solve it? Let's see example. Let's see something look like this. Y prime, yeah, equals negative y plus u3t. Y0 equals 2. Okay, so we're taking the activation and we just multiply the activation by 1. So let's just don't do it. Now, what's special about this one? Well, from 0 to 3, it's y prime equals negative y, y0 equals 2. From 3 to t, 3 to infinity, this one becomes y prime equals negative y plus 1. Y3 equals, we don't know. Okay, so now if I just go ahead and try to say, hey, can you draw me the long-term behavior of this one? This is usually what we want to do, right? Long-term behavior. Or let's just call phase line, equilibriums, those kind of things, right? You can always have those kind of things. Well, what's going to happen? Well, for the first dynamical system, how do I do it? Here, I have 0. Above 0, it's negative. Below 0, it's positive. From here, you can see this one is going to have an equilibrium like that. And you have a lot of different kind of ways of doing it. Okay. What about the second one? Well, the second one has something similar. Better use this. Okay. Now, which behavior do you have? Well, you have two possibilities. Number one, if you're above, you're going to decrease all the way to here. Number two, if you're below, you need to actually increase from here to here. Okay. Now, which one are you going to get? That's the part you don't know. Why? Because it depends on your initial condition. But for the second part, your initial condition happens at 3. Before that, it's a different dynamic. Okay. In other words, you need to know where you start. Did you start here or did you start here? In another way to say, you need to know this number. But how do you know this number? You have to solve this one. Find y3. Sounds good? And that is a big problem. Why? Because with all the qualitative analysis, we were trying to see the long-term behavior without having to solve the equation. Why? Because in general, solving the equation is hard. Make sense so far? If you think about it, there is a lot of functions we cannot solve, but somehow we can talk about equilibriums. Why? Because you don't have to actually technically solve it. But now, to know the dynamic of this one, especially to know the second half, you have to solve the first half. You cannot simply just do the qualitative analysis. You have to know the exact solution. You have to know what the answer is at 3. And that is difficult. Okay? So this one creates a difficulty in qualitative analysis. Okay. Everything we had done before, we were trying to take a shortcut by analyzing the whole thing without having to solve it. Now there's no solution. You have to solve it. Okay. Otherwise, you don't know how the second part is going to play. All right. That's the difficulty. Plus, when you try to solve it, of course, you need to do it piecewisely. Okay, do it piecewisely, of course. Which is another additional trouble. Just like when you do something like this. Okay. What you really don't want is actually, you don't want to actually put it apart and do them piecewisely. It's additional work. You really wish there is a better way of solving it directly. Okay. And that is where the Laplace transform comes into play. This is an example, all right? That is the heavy-sided function. Now let's see how can we handle it with Laplace transform. Okay. Can I do the Laplace transform? So far, so good. SLY equals minus y0, of course, equals negative ly. First difficulty, I do not know the Laplace transform. Okay, we only know exponential. Then the question becomes, can you find the Laplace transform of this? Well, let's do it. UAT is either 0 or 1. So I can split it from 0 to a, and then I can replace it by 0. And you can see this whole thing is 0. Plus from a to infinity, I can replace it by 1. Okay? With that in mind, you know how to do this. Okay. This part will be 0 or infinity. And of course, we don't want this case. So first, this is doable. Here's it should be a. If s is bigger than 0. Okay, we have the Laplace transform for the Heaviside function. Then if we continue with what we have here, we will be able to put something here. That is going to be e negative 3t s divided by s. Okay, so the first obstacle solved. Now go ahead and try to solve Ly. This is 1. Somehow something's wrong. Why? Okay, because the initial value is 2. That's why. S is minus 1. All right. If that is okay, let's try to do the inverse Laplace transform. The first one, super easy, e to the t. Did I copy things wrong? This is plus. I just keep doing that. Okay, e to the negative t. That's the first term. The inverse transform of this. Now we are familiar with that. That is going to be let's see, where is this? We know the first part is good. Okay. I'm really not like this, so I can and do partial fraction. 1 over s minus 1 over s plus 1, which is e to the negative 3s over s minus e to the negative 3s over s plus 1. Partial fractions still work. Good news. This goes to e to the 3t. u3t. We just prove it, right? It's e to the negative as divided by s. So this is going to be e to the negative 3s. That's u3t. The only thing we don't know will be this part. Okay, so the key, what is this? Moreover, we can split it into e to the negative s times 1 over s plus 1. We probably want to focus on this, which we know goes to e to the negative t, but what does this part do? So eventually, if you decompose everything, you started from here, you find the first term is super easy, done. The second term is hard, you do a partial fraction, find the first part of the second part is easy. The only thing left will be this. This we're decomposing into e to the negative s times 1 over s plus 1. Now we want to focus on this and try to see, okay, what does this e to the negative s 3s do? Once we figure out that, this one will be a variation of what we have here. Not the same, but a variation. Okay. Is everything here clear? Let's stop here for today, and let's continue. Let's continue after Thanksgiving. Okay, no classes on Wednesday.